So yeah, we're pleased to have Tom Solomon from Bucknell. Tom is really widely known and well known internationally for his work in nonlinear science. You can think about that. The popular word for that is chaos theory. In particular, what Tom's specialty is doing some very beautiful and elegant work on fluid dynamics and turbulence and connections between those problems in fluids and fluid mixing. So, for example, you put coffee or it's cream in your coffee and stir it up, and you'll see the very beautiful sorts of structures that you'll see between the cream and the coffee. Tom is an expert in understanding how that all connects mathematically in a wide variety of settings, not just in your coffee cup, but in mixing in the ocean, in atmospheric flows, and a wide variety of settings. Tom is also a very elegant speaker, and what he's going to talk to us about is not his research specialty, but a very general talk on the nature of scientific inquiry. And so without further ado, I'll introduce and let Tom Solomon tell us about using science to predict the future, an interactive discussion of induction and scientific reasoning. And let me just, Tom will say this, he'll say, you will welcome questions throughout. If you have questions, raise your hands, and either Dr. Greco or myself will run around with a mic so that can be picked up for everyone as well as picked up in the audio. Okay, so take it away, Tom.
Cool, thanks, Mark. Okay, let's see. Is this working now?
No.
On. Testing.
Testing. There we go. Okay. By the way, Mike was talking about asking questions if you want to ask questions. We're going to go beyond that. When I say interactive, I really mean it. I want you guys participating in this thing. I'm actually going to talk for about 15 or 20 minutes, just some kind of background on how we actually got to where we were. Really talking about the ancient Greeks and Newton and Galileo and stuff like that. And pay attention, because the challenge I'm going to be issuing is going to be relevant to what I'm talking about at the beginning of the talk. And I'm a big fan of bribery. So to encourage people to participate, I have brought door prizes here. So I have 2 blow dart guns complete with suction cups and 5 dunking birds. These things are awesome. They make like great pets. You can have them in front of your computer or something like that. And so the deal here is that the people that, when I get to the challenge part, the people that give me the best responses will win. Good responses will get you the dunking birds, and really good responses will get you the blow darts. So a little extra incentive for you guys to kind of pay attention and actually participate, because the second half of this presentation is a lot more fun if you guys really get into it. You'll see what I mean in a bit, in a moment here. Okay, so let me jump right to the background here. When we're talking about science, these days people often talk about quantum mechanics and relativity and very different topics in modern physics. We're going to go back several centuries, and you might think, classical mechanics, that's boring. No, it's not. And I want to try to convince you otherwise here. Just a show of hands here. How many people here have taken a course that includes classical mechanics in college? Or, raise your hand also if you took it in high school or something like that. Let's go the other way. How many people have never studied classical mechanics, Newtonian physics or anything like that? Okay, so a couple of you, but not that many. Having said that, if you haven't studied classical mechanics, not a problem. The challenge I'm going to be issuing to you guys does not require any previous knowledge of classical mechanics. So here's the first question, and let's kind of, this is what we want. You're not going to win the blow darts for this one here, but I want to see if you guys are kind of paying attention here. Very basic question. What are the goals of science? What do we do when we're doing science? What are the goals of science? Go for it, right off the bat. By the way, I really appreciate people who are volunteering. Go for it.
To understand the world around us.
To understand the world around us. Let me write that down. That's a great response. If I can. To understand the world around us. Next.
To satisfy the human curiosity.
Human curiosity, okay. I think actually human curiosity and understanding the world around us, I think those are related to each other, but I really love that response because that's one of those things that distinctively makes us human beings, that we're curious about how the world is. There's one over there, Mike? Oh, is it here? This is just a warm-up act. This is just a warm-up act.
To improve the human experience.
To improve the human experience. Okay, so there's actually something kind of hidden in that response. Let me write that down. I don't type well when I'm talking as well. To improve the human, what did you say, human? Experience. Okay. Others?
To predict future events.
Excellent. Okay, I was really hoping someone was going to say that one. Predict future.
Donkey bird.
Okay, who was that? Who was that? Where did that come from?
Over here.
Okay, yeah, that merits a donkey bird. That merits a donkey. So we got our first winner of the day here. Okay.
Right down there.
Here, catch this, because it's padded here. Oops, sorry. Okay. Get your efforts. Don't throw donkey birds. Okay, I think that's a really good start here. I've actually kind of boiled these down to two responses here. But by the way, of course, the title of the talk is Using Science to Predict the Future. So I'm glad someone caught that, hey, the title of the talk is relevant to this. Here's how I describe it. And frankly, I think this is basically, excuse me a second, I have something not to run up and down the aisles. To describe how the natural world works. That's really the same response that we had here to understand how the world works around us and to develop a set of laws to predict future behavior. Now, one of the responses that we got to improve human experience is very much related to that second point. Because if we can use laws, if we can write a set of laws and use those to predict how things will work, then we can manipulate those things. We can build bigger buildings. We can make better airplanes. We can make better cars or better computers. This predictive aspect is critically important, and that really is what science does that enables us to improve human existence. Okay, let's move on. Little history. So the ancient Greeks, it's very easy to belittle what the ancient Greeks did, because of course everyone here who has taken introductory physics knows that Aristotle's laws of science were not quite right. But Aristotle and the ancient Greeks did something that's really important. I want to emphasize that this is not a trivial matter at all. The ancient Greeks were the first to say that we can write down a set of laws that can be used to describe the natural world. Now, I've written some other comments on this, but this is really important and not at all obvious. The fact that the universe behaves according to a set of laws, mathematical laws that are predictive in nature, is really not obvious at all. And yet everybody is like, no problem, we just naturally assume that because that's what we're taught. That's not obvious at all, and kind of hang on to that point because we're going to come back to this at the end. So a couple of things.
Here's a question. Why does an apple fall when I release it? I don't have an apple here. That would be kind of gross because it would decay, stuff like that. So I've got a ball with cool spiders in it. You're not winning this one. So if I let go of the ball, it falls to the ground. Why? It's a very basic question. Here's what Aristotle said. Aristotle said he used what we call teleological arguments. And the idea is we're going to actually think about an end goal here for this ball. And the idea, according to Aristotle, is that this ball, or apple, is made out of an element that Aristotle called earth. And earth, anything made out of earth, wants to return back to the earth. So it's a goal-oriented argument that the ball drops because it wants to be back in its natural state. That's how Aristotle argued it. And Aristotle made several other arguments. He said that motion is not a natural state for anything made up of Earth. So the ball wants to be on the ground and motionless. What that means is if I want this thing to move, I have to actually exert a force on it, and it has to be continuing. Well, so I'm actually moving across this lecture hall here. The only reason I'm continuing to move is because I'm continuing to exert a force. The moment I stop exerting, I stop. It's actually not that outlandish an idea, even though it's wrong. Even though it's wrong. Here's some other things he said. The Earth's at the center of the universe. Now, it's very easy these days to kind of belittle that. Of course we know Earth's not at the center of the universe. But there were actually some very compelling arguments for it. And if anybody's curious later on, I can convince you that, in fact, the Earth really is at the center of the universe. But I'm not going to do that now. What Aristotle actually said is that if you think about the planets and the stars, these little dots of light up in the sky, these things are made out of something called ether. And anything made of ether, instead of trying to be on the ground, it goes in perfectly circular orbits. That's what Aristotle said. And it's a compelling idea. It turns out to be wrong. But there's a big issue here with ancient Greeks. They felt that you've got the Earth, and all of us down here on the Earth, and apples and balls and things like that. But then if you go up in the sky, in the heavens, when you think about it, they said there's no reason to believe that the laws that describe an apple near the Earth are any way related to the laws that describe these little dots of light, the stars and the planets. It's actually a perfectly reasonable statement. Again, it turns out to be wrong, but that was their view. Flash forward. Bacon. Francis Bacon. He argued that if you're going to come up with a set of theories, by the way, this is a long time after Aristotle. If you're going to come up with some theories, you must test them experimentally. You've got to do an experiment. And he had this idea of a crucial experiment, something that can distinguish between two competing theories. I have one theory, there's another theory. Give me an experiment where these two theories predict something different. And this is really the beginning of modern science. And I want to emphasize that this is really important. If you want to do science, and you want to come up with a scientific theory, that theory must predict something. The scientist must be able to go to the experimentalist and say, do this experiment, here's what I predict will happen. If that doesn't happen, I will admit my theory is wrong. That's an idea of falsifiability. And if you're not prepared to say if you're not prepared to admit that your theory is wrong, if it disagrees with the experiments, it's not a scientific theory. And I think that's actually, in my opinion, one of the most fundamental differences between science and pseudoscience or superstition. Questions about this point? That's an important point. Okay, flash, not that much more. Galileo. In my opinion, Galileo really was the first experimentalist. He actually put Aristotle's theories to the test. So here's what he did. I think everybody knows about this. He invented a telescope. He looked at Jupiter. Here's what he saw. He saw Jupiter and these dots around them. And then a little bit later, the dots had moved. Later still, they had moved. He found some of these dots. Look at the E here. You look at that E there. It goes to the right, then it comes back to the left, goes on the other side. These little dots are moving back and forth, and Galileo realized, wait a second, something is circling around something else in the sky. And also, I'm not going to go into details of the phases of Venus. Basically, these telescopic arguments basically gave some strong ideas that the Earth really isn't the only thing that things rotate around. Now, Galileo also did some other things. He did some experiments with rolling balls. And what he found is that if you had a ball rolling down a ramp and then up another ramp, he found that the ball would return to the same height. So Galileo then said, well, look, what if the bottom ramp is just horizontal? It'll never return to the same height, which means the ball will keep going and going and going. I.e., objects in motion continue in motion unless acted on by some agent. This is in direct contradiction to Aristotle's results. But the key thing about this is Galileo used experiments to demonstrate this. And that's really important. So basically, he falsified Aristotelian laws, showed that they don't work. Remember, science must be predictive. If you predict something and the experiments disagree with it, you say the theory is wrong. Galileo showed that for Aristotle. So now we have to replace it with something else. And here's where Newton comes into play. Isaac Newton, I think that since most of you have taken classical physics, you know, everybody knows who Newton is. Isaac Newton was really the man. The guy was about as awesome as it comes as far as science is concerned. He came up with what everybody now knows, the 3 laws of classical physics. The law of inertia, by the way, really Galileo mostly had that. The one key thing that Galileo didn't get is he didn't get the idea that circular motion requires acceleration. But Newton basically codified that. Newton's second law. The most important equation in the history of human civilization. That is not an exaggeration. I dare anybody to give me an equation that's done more to change human civilization than Newton's second law has. This is very important. Of course, a lot of you are already familiar with this, but Newton says, no, if something is moving, it stays moving unless a force causes it to accelerate. And if something's stationary, you need to apply a force to cause it to accelerate. Quantitative, predictive relationship here. And Newton's laws stood up when the experiments were actually done. Now, for those of you who have not taken classical physics, I want to emphasize that acceleration is a change in velocity per time, where velocity is both speed and direction. Newton's third law, action-reaction, I'm going to skip it. It's important, but it's not important for this talk here. So here's the question. Looking at the moon. Again, I'm just trying to make sure everyone fully recognizes how amazingly awesome Newton was. Okay, I'm going to take a yo-yo here. I'm going to ask for some participation on this. I'm going to take a yo-yo, I'm going to twirl it in a circle. So this yo-yo is moving in a circle. According to Newton, circular motion, the speed can be constant. It actually isn't, but let's say it were. The direction is changing. That means that there is an acceleration. If there is an acceleration, F that equals ma, there must be a force. What's causing the force here? Just yell it out. Well, it's somewhat in my hand, and actually the hand, indirectly, I heard some other people say the string. That's correct. I mean, the string is pulling on the yo-yo. That's what's causing the acceleration. Now, what about the moon? What about the moon? Newton looked at the moon. He saw the moon is moving in a circular orbit. That means the velocity is changing. That means there's a non-zero acceleration. That means, according to his own principles, the net force must be non-zero. So what is causing that force? Now, probably all of you know the answer to this question, but this was not obvious in Newton's time. Newton did something that Aristotle didn't. He looked at an apple dropping near the earth. He said, look at this. This thing is initially motionless. It's now moving. There's an acceleration. There must be a force acting on it. But there's no spring pulling on it. And there's no spring pulling on the moon. Maybe it's the same effect. And this is where the idea of gravity came from, that there's a universal force, we call it universal gravity, that every pair of objects in the universe experience this mutual force of attraction. Every pair of objects in the universe experience this force of attraction. Now, Newton was amazing. He actually took the data from the time about the moon's orbit. He calculated the acceleration. He then looked at the acceleration of an apple near the Earth, and then looked at the differences, the ratios of the distances, and from that flimsy data, figured out the 1 over r squared dependence here. Really amazing, amazing work. By the way, a cool thing about Newton is that he actually didn't publish this for a while, because there was a half of 1% error in his calculations. He said, it's not holding up to the experiment. I need to figure out what's going wrong. It turned out that the data was off by 0.5%. Newton's predictions were absolutely correct. One more cool thing about Newton. And by the way, he also uses to describe Kepler's laws. So basically, Kepler's laws come out of basically his law of universal gravitation and basically the second law of classical mechanics. So here's the question. Oh, by the way, I want to go back here for a second. When Newton was able to show that Kepler's laws come from his own theories of classical mechanics and law of gravitation, what that does is it basically it demonstrated that the entire set of body of theory was correct. But Newton was still unsure. And here's the question. When you look at the apple, so why does an apple fall? So here's Newton's answer. This is what you might call a mechanistic argument. Newton says the apple falls because there's a gravitational force on the apple. If there's a force, there's an acceleration. And that's why the apple falls. You don't have to think at all about where the apple is going to end up. It's an argument that's based on what the apple is doing right now. There was a problem. Newton recognized that, in fact, there's not just one force acting on the apple, but the apple. So if I take this ball here, there's a force on the ball from me, from you, from the table here. There's a force on the ball from all these different things here, and yet we can treat it as though the ball is experiencing a force towards the center of the Earth. How did Newton show that this still works? Anybody know the answer to this question? Just yell it out if you know it. How did Newton show this works? He invented calculus! Yes. By the way, think about this. The guy invented an entire new branch of mathematics to solve this problem, to prove that the sum of all these almost infinite number of forces is that you can be thinking of it as a single force towards the center of the Earth. Now I want to emphasize here that Isaac Newton, his work was tremendously important. And so just a quick overview of him, of his work. So he has this complete set of laws that seems to describe absolutely everything. And I cannot overstate the importance of this, because this really led to modern technology. Any engineers in the crowd here? Everything you're doing dates back to this. Everything you're doing here dates back to this. His work really enabled the modern era to start here. Oh, and he also developed a new branch of mathematics along the way. So this really led to an explosion, not only in applications, in industrial applications, but also this idea that science can do anything. That's how we improve human existence. Someone commented that a little bit earlier. We use science to improve human condition because of this tremendous predictive power. Now I'm about to issue a challenge here. Are there any questions or comments before I do that? Okay, here comes the fun part. Here's what we're going to do. I am going to pretend in a minute that I've lost all of my memory, except that I still retain, let me break the screen here. I still retain the ability to talk and reason. Other than that, my memory is entirely gone. I'm going to take this ball, I'm going to hold it in my hand. I'm going to open up my fingers, but I don't know what's going to happen. I don't have any idea what's going to happen with the ball when I open up my fingers. Here's the challenge. I want you guys, or one of you, to tell me what's going to happen when I open my fingers, and to convince me that what you say will happen will, in fact, happen. Here's where we get to the door prizes here. A couple ground rules. Ground rule number one, you can ask me to do experiments. You can say, Tom, I want you to try this or this or this. You can pretend that I have equipment that I can use to do whatever kind of measurements you want me to do. But you can't make me violate the laws of physics. You can't make me do an experiment that physically can't be done. You can explain anything to me, and when you explain anything to me, I will then remember that for future reference. Those are the guidelines here. Any questions about what I'm asking you guys to do before we go into the challenge here? Okay. Widen my memory. I have no memory now. I can still talk. Tell me what's going to happen. Who wants to go first? Donkey bird for the first person that takes a shot at this. Okay. I do remember donkey birds, by the way. I'll never forget donkey birds. Okay, back to wiping my memory.
Can I have you do an experiment
You
first?
can have me do whatever you want me to do.
Okay, can you jump up as high as you can? Okay, would you say the ground beneath you is the earth?
Do you want me to call the ground the earth?
Yeah.
Okay, so we're going to define this thing, the earth.
Yeah.
Okay. So,
Would you say that you're smaller than the earth? You have less mass?
are you defining the earth as this little tile beneath me or the whole room? What are we defining the earth as? By the way, this is not a challenge. This is not a trivial question here.
Yeah, so let's say everything that is not a part of you and not a part of me is the earth. So everyone else is part of the earth. We
So
can see
this person's earth.
Yeah.
Your earth.
Yeah.
Okay.
We're all part of earth, except for you and a part of the ball.
What's special about you? Why aren't you earth?
And the microphone.
So anyone who has a microphone isn't earth. Okay. So, I have a microphone too. Where are we going?
Okay, so you don't have a trampoline, but if you had a trampoline, there's this big thing called a trampoline. So if you had a trampoline, can you imagine you're standing on a trampoline?
I'm going to pretend that you explain to me what a trampoline is, because that will take the entire rest of the hour to explain it. Okay, you explain to me what a trampoline is. I'm fine with that.
Okay, so you would place, your imaginary experience, you would place the ball at the edge of the trampoline, and you are standing in the center of the
You want me
trampoline.
to do that? I can pretend I'm doing that.
Yes, yes.
Okay. I'm at the edge. So that's at the edge. I'm in the center.
Okay, so the experiment's happening, the ball has fallen towards you.
What? It's
That's,
sitting right there.
but you're in the trampoline.
Okay. So why
The ball has rolled down to
Oh,
you.
it's rolling towards me.
Yes.
Oh, got it. Okay.
Yes, okay.
I got it.
That is the observed fact, yes.
Okay.
So we can explain that when you drop the ball, you're now not on the trampoline, you're holding the ball. If you were to drop it the same way that a trampoline curves part of this, oh, can we assume that you know what space is? Should I explain what space is?
That's getting tricky. You're talking like relativity here and stuff like that?
Maybe?
Let's not quite go that complicated. I mean, I just saw the ball rolling down towards me. That helps.
Okay. So you are larger than the ball.
Okay.
Yeah. In the same way that the earth is larger than that ball.
Okay.
Yeah. So let's say that the earth is like,
By the way, I want the rest of you guys to be thinking arguments here, because we're not going to be done here.
the earth is in space, which you don't have to know what it is. Earth exists.
Okay, where are we going with this?
And it is in space, and space, just like the trampoline, curves. Because Earth has mass. Just like the trampoline curved, because you have
You lost that. I have no idea what you mean by mass.
you exist and you are made up of stuff.
Okay, I'm fine with that. I'm fine with that.
Okay, the Earth exists and is made up of stuff.
Okay, so mass is stuff.
Mass is stuff.
Okay.
So that ball and the Earth,
This is stuff.
yeah.
Okay, so this has mass.
That, so stuff number 2, the ball,
Okay.
falls towards the Earth, just like the ball fell towards you in the trampoline.
But the Earth is different than a trampoline. The Earth is this ground, this person here, this person here. Trampoline's this big bouncy thing. It's very different. Did anybody else want to jump in here? By the way, thank you so much. By the way, if I disagree with your answers, please don't take offense to that. That's part of fun of this. I really appreciate people taking a shot at it. This is not a trivial issue. Fire away.
Okay, so do you remember when you jumped earlier?
Yes.
You saw the jumping in to look down and notice where the Earth is moving relative to you. So, well, Earth is, well, let's just say Earth is below you right now. Earth is the floor. Earth is everything on the ground.
Is it still these two people?
No, people are no longer Earth. It's just what's below us. So the ground. Earth.
Okay.
All right. So jump again and look at Earth while you're jumping.
Earth is belief. Okay.
Okay. So you saw Earth move away from you and move toward you, right?
Yes.
Okay. So now pretend that you're the ball looking down at Earth and let go of the ball.
I'm the ball looking down at the Earth.
Okay. All right. Let's say.
You want me to put a camera on the ball?
Sure. Put the camera on the wall and then drop the ball and then pretend that it's
What do you mean by drop the ball?
open your fingers.
What's my fingers? Okay?
Okay, so from the camera's perspective, did the Earth get closer to the wall and then move away?
Yes.
So that's the same thing as when you jump, when the Earth moved away and moved back to you. So something is making you move towards the Earth, just like something's making the ball move. So that something is a wall. Okay. So yeah, there's something that's making you move towards Earth. Like there's something making the ball move.
But I was moving away from here. Initially.
Okay, all right. So then pretend the camera's below the ball. Put it like do that to the ball. Do that. And let go. Open your fingers. Okay, so that time the ball moved away from the Earth like you did, but then it also moved back.
Okay?
Just like you did.
So when I threw the ball up, it came back down to me.
Right.
What's going to happen next?
Next, it came. Well, okay. I'm having trouble explaining this.
By the way, these are all great answers here. We're getting closer and closer and closer. It's going to take a little while. Okay, go for it.
I have a question on the rules of this game.
Yeah, fire away.
Are we trying to prove that it's going to fall, or are we trying to tell you why? Because, like, if you're going to ask, like, why gravity happens, like, sure, I know it's there, but, like, I don't think anybody really knows why the gravity's there.
You have to convince me.
You
You have to convince me that's going to happen. Don't just tell me what's going to happen. You then have to convince me why it's going to happen. And you need to convince me that it's going to happen. That's the rule point. So they're just saying, tell me out here, just saying the ball's going to drop. That's not enough. I want you to explain to me and demonstrate to me that's going to happen. Give me a credible argument.
If we're only operating on stuff that we can have you experimentally do, why don't we have you do an experiment of dropping a ball then?
Tell me what to do.
Drop the ball. Like we did before.
Okay? Got it.
If you repeated that an endless amount of times, it would always happen the same way, and you can test that. So, I mean, isn't the idea of a law of physics just something that, when it's experimentally tested, like, nobody can prove it wrong?
Well, but time out here. These are great comments you're making, by the way. It actually turns out that you can never actually prove a law correct. You can only falsify it, but you can have experiments that agree with it so often that you basically elevate your theory. Having said that, you're on a good track here. Keep going.
So it's kind of impossible to prove that it's going to fall then. By that
But
definition.
by the way, there is an argument that will convince me. I am not issuing a challenge that has no possible result. There is an argument that will convince me. There is an argument that convinces me. Having said that, you are really, really, really on the right track here. Let's take this over here.
I don't have any actual good ideas about how to prove this though, so.
No, you're on the right track. Or actually, you can hand it like whoever wants to. Whoever has a kind of.
So the only real argument I could give is that during the 10,000 of years, people have done these experiments, millions of people, and it was always the same result. That the thing fell down towards the earth. So if this convinces you, then...
Okay, so I don't know about the history here. You can tell me to do some experiments if you want.
I don't know what will happen for sure when you release the ball, but according to experience, this is what happened always. So we think that the ball will do the same thing.
Let me see if I understand you then. You're saying that in the past, people have done this and the ball fell. So in the future, the same thing should happen? Okay. Hang on a second here. That's the first key element of the argument. I'm going to take a time out here. So I've got my memory back. Induction. This is a statement. that if something happens a certain way in the past, by the way, you were basically getting at this point as well. That's why you got the donkey bird here. If something happens a certain way in the past, if something happened a certain way in the past, then the same thing will happen in the future. I'm going to be a little bit more specific about this. If, in the past, cause A resulted in effect B, then we make the statement, using induction, we can say that in the future, if we set up an experiment, this is your point here, if we set up an experiment with the same cause, we'll get the same effect. So you're arguing that in the past, when people did this, the ball fell. So I should believe that in the future, the same thing will happen. That's the argument of induction. Why? Why should I believe that if this happened this way in the past, the same thing will happen in the future? Wiping the memory again. Let's go farther here.
It's a lot. We should believe that things will happen in the future the same way they've happened in the past, because that's the simplest thing to believe. Any alternative?
I can give you something simpler.
Okay.
I'm going to believe that nothing will ever happen. That's simpler than saying all the same things will happen. There's simple ways of arguing it. There's simpler ways of arguing it.
So if anyone had ever argued that in the past, they would have been wrong.
Okay, I want to comment about this. And by the way, I love that argument. I love that argument. Here, let me restate this, and tell me if I'm restating this wrong. Here's how I'm interpreting you. We should, by the way, this is what we're really doing here. The question here is, why should I accept induction? You're saying we should accept induction because it's always worked in the past. And since induction always worked in the past, it should work in the future. So it's using induction to prove induction. I'm not taking that. Another side here. David Hume. Awesome philosopher. He argued there is no proof for induction. So why should I accept that the ball is going to fall? We're getting really close here. There's actually several hands here. There's one back there. Oh, yes, Becky.
Okay, drop something else.
Tell me what? Not the donkey birds, because they break. What's that? This?
Sure.
Okay.
Do you think that's going to go up?
I have no idea what's going to happen.
Drop it. It goes down.
Okay. But that's different than this.
Yeah. Hold them both at the same height, and then drop them both. And in my opinion, that's never going to stop happening, and I don't think that you can prove me wrong.
I admire you changing the challenge here. I asked you guys to convince me. You're saying, I'm not taking that. You have to convince me that I'm wrong. Which, by the way, you get the other donkey bird on the table. Just for the sheer chutzpah of doing that. Having said that, no. That's not the challenge. The challenge is to convince me. There's an argument that will work. There's an argument that will convince me. Back there. Oh. Sorry, I'm pointing the people, and poor Mike has to get over there with the microphone.
Okay, so a couple days have passed since you wiped your memory now.
Yes. By the way, I remember everything in this conversation, and everything we've done.
I explained to you that the sun was the giant ball of fire in the sky.
Okay.
And that humans require warmth to live.
Okay. Is that related to this?
Sort of, yes.
Okay.
and every morning you looked over and the sun rose, and then 12 hours later the sun set.
Got it?
Tomorrow
I've
morning.
done that experiment. I'm with you on that.
Tomorrow morning, is the sun going to rise?
No idea.
Okay.
By the way,
Are you clear on the fact that the sun is necessary for human life? Okay, the sun is necessary for human life.
Fine. Fine. I don't have to do with this. You're trying to get to induction, okay. By the way, time out for a second. I live on a planet orbiting a large star. Every day, for 1 billion years, the sun rises in the morning. So I assume, since it always happened, that will always happen again. Guess what? One day the sun supernovas. And the next day, even though it happened 50 billion times, the next day it didn't happen. So the sun rising in the morning is not going to convince me.
Okay.
The sun rising in the morning is not going to. I'm going to turn up the heat for here for a second. Because I want to get towards our conclusion here. This is the basis behind all of science. You do not have science without induction. So you need to save the entire field of science with this argument. And it's even more than that. Everything that you do every day of your life is based on induction, is based on something that Hume argues cannot be proved. Everything you do. When you get to a street and you see cars going by, you don't walk in front of them. Because in the past, when someone does that, they've been squished. And you assume that if you do that in the future, you'll be squished too. There's a particular flavor of ice cream that you go to get. Because in the past, it's tasted good. So you assume, by induction, that in the future, it will taste good. You take showers in the morning because in the past, you've seen that people that don't take showers stink, and you don't want to be a stinky person. You get out of bed in the morning because past experience tells you that life sucks in the past for people that don't get out of bed, and it's much better if you do. So without induction, there's no reason for anybody to do anything in their lives. Somebody, please give me an argument about why I should accept induction as valid. Get back to the simple thing here. I think it's simple to say that nothing exists. We get one of these hands here. There's an argument that will convince me.
All right, so pick up the ball again.
It's not going to be a picking up the ball argument. Oh, darn. Yeah, actually, since we're running short on time, it's not going to be a picking up the ball argument. There's an argument that will convince me. Come on, let's get it.
So you keep saying you don't know anything, right?
Well, I now know all of the conversations we've had. And because of this guy here, I know that in the past, every time someone's done this experiment, the ball was dropped.
Okay.
So I know several things now.
Yeah, but anything that you haven't observed, like you don't know that.
Yeah, you can tell me that. And you can say, pretend you understand distance.
Well, yeah, but I mean, I think my point is that, like, I think certainty is impossible.
Okay.
And I don't know if I can go through. I'm hoping you already agree with me, because you're saying like, oh, you can't be certain of anything until you see it.
You're already sitting there with the donkey bird. You're already sitting there with the donkey bird in front of you, so you know that I've actually been pretty keen on what you were saying before.
Okay, so the point is that everybody wants to live, and I think that part of any goal of science is to like improve their life. And so you're always going to go, if you can't be certain, with the thing that's most likely to happen. And so induction, if you're thinking probabilistically, is the most likely thing based on what you've seen in the past. I think that's a good probability.
I'm going to counter that argument. Here's what you're saying. In the past, it was overwhelmingly probable that the ball would drop when I opened my fingers. So therefore, in the future, it should be overwhelmingly probable that the ball will drop again. It's still an induction argument.
No, it's kind of just like it's the best you can do, I think, is the argument.
Very close. Very close. I'm looking at your comment, your comment, you guys are both super close to convincing me. Super close to convincing me. There's some other hands up here.
Can I just add to what my friend over there said and say the ball always dropped in the past and there are some few, as long as there are few parameters that do not change. I mean, the sun is always going to rise unless there's a supernova. Unless my parameters change, the ball is always
I'm going to give you one more unless. Unless every law of physics changes at this instant. Well, I don't know if everything's predictable. So the unless argument doesn't work because how do I know the laws of physics aren't going to just dramatically change in the next minute? Let me phrase the question differently here. Why do you guys get up in the morning? Why do you take showers? Why do you, I mean, how many people here believe induction? Tomorrow morning, are you going to get out of bed? And you believe induction. Why? Somebody, gotta give me a good argument. Let's do rapid fire here because you're going to either get this quickly or you're not. Let's just go with whatever hand. Why don't you go with quick?
Because every other prediction you made has been falsified.
I'm not going to take that. I'm not going to accept that because in the past they were all falsified. The laws of physics may change tomorrow. They may change right now. Next, another hand, go for it.
Because we have faith that the universe obeys laws.
Here's the argument. Because we're screwed if we don't. Because we have no choice if we don't. So here's what I'm going to do. Hume says this can't be proved. I don't care. I'm going to accept induction without proof. That is faith. You use the word faith. That in my, faith, some people talk about faith as belief in God. I say faith is belief in something even though it doesn't have a proof. So your argument to me is I should just accept it even though I can't prove it. And that's what convinces me here. Now, you might think, and I hope some of you are thinking, no way. There is no way I'm going to accept that science is based on a faith argument. Guess what it is? It is. Read Hume's work. He issued a challenge to philosophers. He said, someone come up with a proof for induction. Nobody has succeeded in matching Hume's challenge. Nobody has succeeded. Now, does that mean that people shut down science? No, not at all. In fact, scientists are perfectly happy going on. I am perfectly happy. Even knowing Hume's results here, I am completely, 100% comfortable with induction. And the reason I'm comfortable with it is because I'm screwed if I'm not comfortable with it. I accept it on faith, even though there is no legitimate logical proof for it. The reason why I like commenting about this is that there is this kind of common view that science is completely logical, completely rational, and it is. Science really is the best method that we have for understanding how the universe works. But there's this one piece to it that can never be proved. And you have to say, so be it. I don't care if there's no proof. I'm going to accept it because I want to accept it and because I have no choice but to accept it without proof, i.e., I'm going to accept it on faith. Now, I want to go back. By the way, it turns out that induction actually isn't true. How many people here have studied quantum mechanics? We know in quantum mechanics that at the quantum level, if you do an experiment, fire a particle, an electron or a photon through a two-slit apparatus, it goes bing on a screen behind there. Do exactly 100% the same experiment again. That electron's going to pop on a different location on that screen. Now, this is not an entire violation of induction, because you can turn around and you can say, well, quantum mechanics says that Cause A won't cause exactly the same effect B each time you do it, but there's a probabilistic aspect of it. And by the way, like I said, you two are like really right on top of the issue here. So you can say, well, induction still works from a probabilistic perspective in quantum mechanics. But why does induction work in this universe? If you think about it, there's no logical reason why it should. The universe didn't have to obey laws of induction. Aristotle's argument that the universe can be described by a set of laws. There's really no reason why that has to be the case. And yet it is the case. And so my absolute favorite quote, and I think this is something, if I leave you guys with this particular comment, I really hope that this kind of sinks here. Einstein made this comment that what is inconceivable about the universe is that it is at all conceivable. This is something that we all take for granted. We all take for granted that we live in a universe that can be described by this beautiful set of laws. And we can use those laws to predict things. There's no reason. There's no reason why the universe has to follow that. And yet, it does. And that's really, really cool. That's really, really cool. There's no reason why induction has to work, and yet it does, for the most part. Any questions or comments?
If the solution to the problem is that we just have to accept it because it's easier that way, doesn't that end up being Occam's razor?
Well, okay, so this is, by the way, I will tell you, actually, your answer, which was earlier, pretty much, you kind of had it already. But I wanted to draw it out a little bit more. It's not so much that it's the simplest answer, because I still think the simplest answer, if you're talking about Occam's razor, I think the simplest answer, frankly, is that there's no reason why anything has to happen. But I think you can use Occam's razor argument. It's still not a proof. Occam's razor, there are plenty of cases where the simplest answer is not the right answer. So Occam's razor, I think, is a great argument, but it's not a proof. So I wouldn't have accepted that as a proof. But it's a very good argument. All right.
Why can't we deduce these things?
Why can't we deduce these things?
Why can't we deduce that A causes B rather than induce?
Because it's not always true. I mean, so I can easily. So by the way, in the quantum example, I'm going to give you an example of the situation where A didn't cause B all the time. So the firing the particles through the two slits. Firing the particles through the two slits does not always mean the particles will land in that particular spot. So there is actually experimental evidence that cause A doesn't always result in the same effect B. I can also argue that I can easily imagine a universe. Where cause A does not always result in the same effect B. So if I can imagine a universe that does that, that means it's not necessarily the case. So deduction alone is not going to be good enough. It's not going to be good enough. Other question? I know it's 8 o'clock, so I'll let people go. Any other questions?
Is it a coincidence that the Enlightenment happened around the time of Newton? That the idea of laws as human affairs and orderly societies, was that a reflection of what Newton was doing in different comments?
I'm going to admit ignorance on this. I'm a physicist. I think that's a great question. And I think really we need some social scientists or humanists to answer that question. I think it's a very compelling argument, but I simply don't know the answer to that question. I mean, I think it certainly makes sense. It certainly makes sense, and it certainly didn't harm things. I mean, this idea that these rational set of laws are so successful, it certainly didn't harm the Enlightenment. I think it's certainly a big aspect of it, but I can't say for certain. Good question. Should we stop there? Ed, I'm going to leave it to you to just cut me off whenever you want to stop.
Let's give our speaker a round of applause.